e passo para o meu colega, professor Alexandre Simons, para moderar a sessão 2. Por favor.
Bom, obrigado, Segem. Vou lembrar a audiência, primeiramente, bom dia ou boa tarde a todos. Só lembrar a nossa audiência aqui em português que esse segundo painel será feito em inglês, né, em função dos nossos convidados e dos nossos apresentadores. Ok? Então, agora eu vou shiftar para o inglês para a gente iniciar a segunda sessão. So, thank you everyone for attending. Thanks to all our presenters today. We'll start as Segem said, we'll start the second panel or second session of our event. We will have in this second panel 6 presentations, again, as in the first part. But this time, they will cover, I think, a wider range of topics, touching not only offshore wind, but also marine energies in general, which is a very interesting topic for us and for the naval architecture and marine engineering community, for sure. I want, once again, to thank all the speakers. I am sure all the presentations will be very interesting for us, but I have to remind you that we are on a tight schedule. So I ask you, please, not to exceed the 20 minutes slot for your presentation. And if possible, it would be very nice if you could save us a few minutes in the end, so I can select a couple of questions from the audience, so we can have a brief debate here. In case there are more questions than that, I will kindly ask the presenters to answer the questions later in the chat or in the Q&A of Zoom. Okay. So no more time to wait. Let's move right on to our first presentation, which will be given by Ana Brito e Melo. Dr. Ana Brito has, from WAVEC, Dr. Ana Brito has 28 years of combined experience in the sector of marine renewable energies, of which 8 were research focused and 20 years in projects to private clients and organizations, as well as top-level management activities. She has a PhD in mechanical engineering in the team of wave energy numerical modeling. She joined WAVEC in 2003, being responsible for securing and executing services to the industry, governments, and public bodies. During the period 2012 to 2019, she was executive director of WAVEC, and in 2020, she became responsible for strategic studies and senior advisor of the board for communication. She also holds the position of executive secretary of the IEA Ocean Energy Systems Program. Please, Anna, go ahead.
Hello to all, and thank you, Alexandra, for the introduction, and also thank you for the invitation to attend this session. I will focus my presentation on marine renewable energies, what is happening in Portugal, and the activities in which WAVEC is involved, which is mainly on the basis of international collaboration. Just one slide. Let's see if I think you see my screen. Okay, second slide was not moving. WAVEC was created in 2003 as a non-profit association, and we promote the development of marine renewable energies in Portugal. We have been expanding our activity also to offshore aquaculture, which is a sector that is starting to grow in Portugal. And we are also involved in several, developing solutions for the blue economy. We have 8 associates here in the bottom of this slide, which are those in Portugal with interest and involvement in offshore renewable energies. Our international collaboration has been done in very diversified topics, but we can group here in 4 different areas on technologies in monitoring, and we have been assisting on the performance monitoring of ocean energy projects, wave tank testing, instrumentation. Another important area is marine environment and public policies. And here we have been involved in developing methodologies for monitoring the environmental impact of marine renewable energy projects, and also much work in Portugal related with public policies. On numerical modeling, we have a team dedicated to studying the interaction between these offshore structures and the ocean, developing tools for assisting in the design of moorings, working with CFD solutions, and also expanding our knowledge more recently to digital twins. On the economy and industry, we work on market studies, economic analysis, and also site selection studies. So this covers our activity, and most of this work done with many international partners. I will briefly present what is going on demonstration projects. During 5 years, we had wind floating offshore turbine of 2 megawatts. So the first pilot project, let's say, installed in Portugal. And we have been in the scope of European funded projects. So with different partners at the European level, we have been involved in the environmental monitoring, public outreach, recommendations for a roadmap for offshore renewable energies, and also analyzing the power production and the performance of this pilot project. Following this project, more recently, the company, the ADP, progressed to a farm. So based on the same technology, 3 prototypes. In total 25 megawatts, and our activity has been related with the consenting process of this first wind farm, public outreach. This is something that we keep, it's very important for projects to take into account that there are potential conflicts of use in the maritime space, and we pay much attention to this topic. Environmental monitoring, because it's important to continue collecting as much as possible data on the impact of these projects in the marine life. And we were also involved in the technical tender for the specifications of the export cable. On wave energy, we have been working with AW Energy, which is a Finnish company developing a project in Portugal, wave roller. They started with a small unit of 100 kilowatt, then they progressed to 350 kilowatt. This is a project since 2012 happening in Portugal. It's a flap anchored on a sea button. What you see here is 3 flaps, and this barge is submerged. And it moves with surge waves. It's a project that was grid connected to the Portuguese national grid, and it's interesting that it was located in Natura 20 area, which means it's a sensitive area from the environmental point of view, and it was needed to do an extensive environmental monitoring. So many campaigns to assure that this all potential environmental impact can be mitigated in future. We also have been involved in the development of a Swedish technology from the developer Companhia. Our activities have been done in collaboration with many partners in the scope of European and Portuguese projects. Wave Boost, iWave 5 are the acronyms of these projects. There's one unit, what we see here, 350 kilowatts, was built in Portugal with Portuguese companies, then was towed to Scotland, to the European Marine Energy Center for the initial tests. And now they are progressing in Portugal with a wave farm, in total 1.2 megawatt. This is a development in which we have been involved since 2013. Another interesting project we have been involved in Pivot Buoy, which is a European funded project that looks into a disruptive floating wind system. It's a downwind turbine with a single point mooring. It involves several partners and is a very interesting project in which the owner of this or the CEO of this company was a previous collaborator at WAVEC. Another interesting activity that involves several partners across the Atlantic arc is the project Blue Gift. Blue Gift is a collaboration between test centers. So EMAC in Scotland, CINO in France, BMAP in Spain, Smart Bay in Ireland, Plocan in Canary Islands, and Central Nantes University also with a test site at SEMREF. So all these partners, they are involved in testing devices, offshore wind or wave energy or tidal energy in test centers. And the project is very interesting for developers because it offers a voucher for any developer willing to be a candidate for these test centers. It will end up in August next year, and several projects could benefit from this voucher. It's starting now, just this September, a new project. It's called EU Scores. And this is a project funded by a program called Green Deal from the European Commission with almost 35 million euros. And the aim is to demonstrate the possibility to combine different resources. So the project will focus on two demonstrations. In Portugal, it will be a 1.2 megawatts wave energy array from core power that I mentioned before, and to show how this can be co-located with a floating wind farm. Another demonstration project is a 3 megawatt offshore solar PV by a developer called Oceans of Energy. This will be in Belgium, and they will show the co-location with the button fixed wind farm. So showing this co-location is doing research on how to share interconnections, underwater interconnections, logistic operations, analyzing the benefit in terms of costs reduction. So all this will be addressed by this project that will run until 2025. Another group of research activities, more generic activities. I will mention here only some examples. DT Ocean Plus. It's a very interesting project that was just come to an end this year. And the suite of second generation advanced design tools have been developed. It's open source. All information, the code is available to be used here in this website, and it can be used for the selection, development, and deployment of ocean energy systems. Many entities were involved, European entities were involved, but not only European, and REL as well was involved in this project. Another project in which we have been working is Blue Cow. Blue Cow is trying to look to how to combine wave energy with offshore aquaculture. So it's using one device here, the oscillating water column, a type of wave energy device, and see how to build a platform that could be used for fish feeding. There were several activities here related with accessing the resource, so that is trying to characterize the fish feeding operation, and came to an estimation of the power that is required for this kind of support to the offshore aquaculture. Oceanic, it's a project that is also was concluded very recently, and here we have been developing and testing innovative and environmentally friendly coatings, so to protect marine structures against marine growth. This is also, it's a project that resulted from the collaboration of different partners and can be used, can be applied for any offshore renewable energy project. In terms of development tools and strategic support, I gave just here an example of one tool that we use to select areas for the development of offshore wind parks or also offshore aquaculture, taking into account the type of the technology and coming to the outputs in terms of the levelized cost of energy, including a financial analysis of the projects. We also have been involved in several strategic studies. Here is an example, technical assistance to the Chilean government, to the Ministry of Energy, so building a vision for Chile on marine renewable energies. For the European Commission, recently we produced a market study in collaboration with an Italian consultant, looking to what are the financial needs if we want to develop the pipeline of ocean energy projects, and here was wave, tidal projects mainly. What will be the needs in terms of public funding to come to this, to realize or to come to this all these projects. So developing scenarios for the ocean energy deployment. Finally, I'm coming to an end to give some time for questions. And I would like to speak about part of my work is dedicated to the IEA OES, which is the Ocean Energy Systems Technology Collaboration Program within the International Energy Agency. So the International Energy have many groups looking to different aspects of energy, and one is dedicated to ocean energy. Within this group has 25 members. Membership is done by government, so it's the government that agrees or that expresses the interest to participate and is invited by the executive committee of this group. We would like much to have Brazil in this group, so I launch here the invitation to contact me if you'd like to know how to get involved in this group. We publish many publications, always based on international collaboration. The latest one that will be released, I think, next week will present 6 interviews on alternative markets for ocean energy. So examples of how to use ocean energy in off-grid markets, for instance. So not the usual grid-connected use. And we published every year annual report that includes a summary of what is happening in each country member. This is only ocean energy, so not including offshore wind, because there is other group looking to offshore wind. Finally, just to tell you that if you want to know more about this, or to know more on marine renewable energies, we are organizing our annual seminar. Every year we do it with an embassy, and this year will be with Japan, so you can learn what is going on Japan and Portugal on 30 November. Alexander, I hope I used my time.
Perfect. Perfect, Anna. Thank you very much for a very interesting presentation, for sharing with us this scenario of marine energy, especially in Europe. Thank you for the invitation, for the participation in the program. Would be very important to have Brazilians joining in, of course. And I think we have time for one question at least. And I will ask you a question that appeared here in the Q&A, which I think, of course, is one that most of our audience probably is making themselves. Regarding the wave energy and some of the projects that you mentioned, if they are commercial projects or if they are demonstration projects at this moment. And I will expand a little bit more on that and ask you if you could share with us your ideas on, because we know this technology is in general with a lower readiness level, at least from the commercial point of view, compared, for example, to offshore wind. And if you could share with us what is your expectations regarding the future of wave energy? Are there opportunities in Europe, at least for not only for small scale projects, but let's say in the near future for medium scale power production, for example?
Yes, wave energy is at a lower stage if we compare with offshore wind, but we have to. But we know that offshore wind is benefiting from the whole experience from the onshore. In wave energy, we have seen that the path to commercialization has taken longer than expected. But because dealing with these prototypes in the open sea has been difficult, as when we go to the ocean, we need to go with the reliable structures and with a certain dimension, and it's difficult to find the appropriate level of funding to develop these such projects. But we have seen many teams, very good teams developing concepts that we believe will with appropriate funding. I think it's always a question of funding, because developers spend so much time finding out the funding they need to go to a project to the water. But we have seen many projects in the latest years that are encouraging us. I think that there are many markets for wave energy. In several countries, water is an issue, and so wave energy projects can be used for desalination, also for islands. If we look into what will be the future, that we will expand activities to the open ocean, observation, and all this will need a source of energy, and wave energy can indeed be used as a source of energy for these projects. At the same level, I think that we will start to develop, for instance, core power in Portugal will be the first wave farm, and this is progressing. I mean, we need to show that the technology is reliable. There is a project problem also of cost. The costs need to come down to be competitive with other renewables. But I think we are on the right way.
It should be optimistic.
Yes, always.
Thank you very much, Anna, for your very nice presentation. Okay. And now we'll move on to our second presentation in the panel, which will be given by Flavia Rezende from Principal Power. I know Flavia from a long time ago. Flavia is a naval architect with 20 years of experience in the offshore industry. Flavia joined Principal Power in 2020 as engineering and operations senior manager. Prior to joining Principal Power, Flavia spent 19 years at Bureau Veritas, where she occupied the position of offshore manager and director of Technical Center in North America. Flavia, please, the screen is yours.
Yeah, thank you for the introduction, Alexandre, and very nice to meet you again after so long time, and some other people that I know that are in the list. I just want to make sure that you see my screen, the presentation mode.
Yes.
Okay, perfect. So that's good. So as you said, I'm now occupying the position of engineering manager for Principal Power. I'm based in France now. So I'm going to present you our latest projects and our vision for the future and where our focus is. Just a word on Principal Power. We are the designers of the floater that you see on the screen that Anna also showed in her presentation. So I'll think I'll be able to spare some time after Anna has presented WindFloat Atlantic project. So I'll go quick there. And also maybe I don't need to repeat what other colleagues probably said, like DNVGL before, and also University of Tokyo about the potential zone of offshore wind, and in particular the potentials of deep water offshore wind. When we talk about deep water offshore wind, differently from oil and gas, we are talking about water depths in the range above 60 meters. So, we believe that there is below 40 meters, the bottom fixed solution is more appropriate, and there is a transitional zone between 40 to 60 meters where both could be interesting solutions. So I think I will not repeat. I have removed the slide about the addressable market because that was presented before in terms of gigawatts, how much it represents in different regions. And I'll go probably straight to the presentation of the WindFloat technology, which is the foundation, the floating foundation that we develop at Principal Power. So I'll give you an introduction of the projects that we have done so far, and briefly talk about the future after that. So the WindFloat technology is a solution based on a semi-submersible concept. The specificities about it is that it has 3 columns, and the turbine is installed on one of the columns, and the reason for doing that is to keep the turbine close to the quay, to be able to integrate it with cranes that can easily reach the column level and install the turbine without having to use installation vessels. So this is a key feature of the floater, to be able to install, as I think I saw in previous presentations, someone, I think it was Dian VGL, talking about how scarce installation vessels are for turbine installation. So it's very important to lower the costs, to be able to install, to integrate the turbine at quayside. We developed the floater turbine agnostic, so we can work with different turbine providers. So far, we have developed the projects based on Vestas turbine with WindFloat Atlantic is 8.4 megawatts, Kincardine is 9.5 megawatts, and the EFGL that we'll see later is 10 megawatts already. The other advantage of a semi-submersible is the stability is independent of mooring lines, like differently from a TLP, for example, where we need the tandems to have stability. And other thing is that the loads on the mooring system is quite low. So we developed the mooring system, we designed the mooring system to have a very low pretension. And then we can install the anchors with conventional tug vessels. So we don't need very large anchor handling vessels. So this is in a nutshell, talking a little bit more about the mooring system, because this is also an important contributor to lower the CapEx. So we base our solution on drag embedded anchors. So for it's a very common type of anchor and very easy to install. We use HMPE, which is for water depths in the range of 50 to 100 meters or more. HMPE has the advantage of providing very high stiffness to the system while keeping the weight very low. Keeping the weight low, as I said, is important to keep the pretension low and make the installation easier. We use also mooring connectors, platform mooring connectors that are quite simple, like ball grab type connectors. And for deeper water depths, we are now moving to systems that are more semi-taut. And also, in this case, we need to have a little bit more elasticity. So we go with normally polyester type of material, and also to limit the mooring radius. And then we go with other types of anchors, like high vertical load anchors, or like plates or suction anchors. So talking about the projects and the path to the technology development, we have started with WindFloat 1 that Anna has presented. It's a 2 megawatt platform. This platform has operated for 6 years in Portugal. It has been decommissioned from the site, and we have refurbished and recommissioned it in Scotland, where it has operated for additional 2 years. So until we have replaced it by 5 platforms of 9.5 megawatts that have just been commissioned. I think I'll show you a picture later. So at this point of the prototype, what we are trying to achieve is to demonstrate the feasibility of the concept. Sorry. Okay, this is WindFloat. So we are trying to demonstrate the feasibility of the concept, the reliability of the reliability of the concept. And we are very happy now that we have gone through all the phases from construction till decommissioning, which helped us to collect a lot of data and to feedback our latest projects. This platform has endured a lot of storms, including wave heights up to 17 meters. Also the latest one, WindFloat Atlantic, that we'll show you, has already gone through a storm last year that is above 1 year return period storm, with the 3 turbines operating during the storm without any issue. So after the prototype is demonstrated, we entered into a pre-commercial phase that we are concluding now, where we try to show the bankability of the projects. So we try to demonstrate not the technical feasibility, but that we can make it with funding, and it can be economically sustainable. So we have in that phase, we are carrying out 3 projects. So one is Windfloat Atlantic, has been commissioned beginning of last year, and is operating since then. KOWL in Scotland has been just commissioned with 5 platforms of the 9.5 megawatts. Actually, it's close to 50, not exactly 50. And we are now concluding the detailed design of EFGL with 3 turbines of 10 megawatts. So total 105 megawatts. This is Windfloat Atlantic project. Water depths range around 100 meters deep. The project has been certified by ABS, and it has been the first bank-financed floating wind farm. This is just let's see if it can work. This is one of a very large storm that hit Portugal 4th December last year, called the Doha, with wave heights, significant wave heights in the order of 7 meters, significant. And we can see that day, you see in the back the turbines spinning, and we can also see the floater behaviors, which are typical from a semi-submersible that is quite good. One of the features of Windfloat is that we have an active system, because you can imagine that during a storm or even during a rated wind speed, there is very high thrust applied to the turbine. So this high thrust creates a very large overturning moment to the platform, and this deteriorates the performance of the turbine. So the active system allows the floater, actually it balances the floater actively, so moving water from one column to the other, to compensate for that action of the wind on the turbine. So you can see that even during this storm, the platforms are leveled and the turbines can operate in a good condition. Windfloat Kincardine has been just commissioned, as I said, this year. We finished the commission of the 5th platform this year. And Éolienne Flottante Golfe du Lion, we are entering to the fabrication, I hope soon. So we are just concluding design, and this project is certified by Bureau Veritas. Here we see in this picture the 5 turbine in Scotland. The sky is not as blue as we see in Portugal, but we see here the 5, and with this project is now, in terms of megawatts produced, it's the largest capacity of floating wind turbine farm installed at this point. So now what's next? I think we have, as I said, we consider that this pre-commercial phase, the phase is reaching an end, and now the projects we are working on are already commercial projects or industrialized projects. So we are talking normally about a number of between 10 and 50 units or more for the industrialized cases. Now we are focusing on a phase where we need to reduce costs and make this scalable. So that is our focus right now, is rather than to prove the concept which is already proven, is to make this concept scalable. So our top priority right now is to optimize the design of the floater, working together with the turbine manufacturer to co-design and co-control the platforms, not looking into an individual platform, but on a farm. So we have projects where we can, for example, optimize the performance of the wind turbine through our control system to lean into to better orient the platform with respect to the wind, optimize, as I said, power production. Also, we have projects where we look into shallow water depths. Shallow water depths, I'm talking about this transitional depths between 40 meters and 60 meter water depths, and also very deep waters in the range of 1,000 or more water depths. We have a strong focus also now on fabrication to make sure that we can assemble easily, weld easily, and roll out. Our goal is to roll out one wind float every 2 days, which is quite ambitious, which poses a lot of challenge in terms of the ability to fabricate, to store, to integrate the turbine, and so on. Just to conclude, we believe that floating wind can contribute and participate in the blue economy and can coexist with a number of other ocean industries, as Anna also said. So green hydrogen or offshore aquaculture, power hubs, and so on. So this is, and we are very happy, and personally I'm very happy to have reconverted to the renewables, to converted myself to the renewables. I'm also a believer, as I think Lara said before, in this industry, and I'm very happy to be part of a company that is contributing to this goal. So thank you so much.
Thank you very much, Flavia, for the very nice presentation, very nice images of wind float and the waves. And well, we're right on time, but I think we have time for one question at least, which would be, I think that for us here in Brazil, Flavia, as you know, most of the attractive areas for offshore wind are in shallow water, right? If you can just comment briefly on that competitiveness around this transitional area that you mentioned, close to 50 or 60 meters maybe. Can we expect in the near future the costs of floating wind to continue to approach the costs of fixed offshore wind?
Yeah, this is our goal. That's what we are working towards. Well, let's say that I think both have their place. As I said, I don't think we should claim that it's competitive. We are competitive. Floating wind is competitive in water depths below 40 meters. In the transitional area, there is a number of features that we can where we can have an advantage in floating wind, which would be in terms of turbine integration, for example, ability areas where there is no there is limited resource for offshore turbine installation, for example, installation vessels, as we said, we can integrate at quayside. Also for turbine during operation and maintenance, one of the features of wind float is to be able to disconnect and tow the platform to do any large maintenance on the turbine. So don't need again have lift vessel to make a maintenance large maintenance on the turbines. And in terms of fabrication of components, that's probably where we need to increase the competitiveness, to become more competitive. But that's the goal. We really need to scale up so that it becomes a reality. So far, with projects in the order of, with 3 or 5 platforms, the scale effect is not there. So I believe that once we scale up, the floating wind can become competitive even for transitional areas because of advantage, as I said here, in terms of turbine integration, intervention, and this type of things.
Okay, thank you very much again, Flavia. It was nice to see you. We'll have to move to our next presentation, also a third presentation in this session, which will be given by Jonathan Boutro from Bureau Veritas. Jonathan is graduated with a master's degree in mechanical modeling of materials and structures from École Centrale Marseille. He joined Bureau Veritas as a structural engineer for different types of offshore oil and gas floating assets. Jonathan is now market leader for offshore wind and marine renewable energies, which main objectives are to support the business development network for market intelligence, prospection, and offers, but also to advise on R&D needs and to ensure a transverse view of all BV activities on these markets. So please, Jonathan, go ahead.
Thank you. So good morning, good afternoon, everyone. I hope that you can hear me well and that you can see my screen.
Perfectly.
Thank you. So I'll talk about the different certification schemes that exist for marine renewable energies, but as you will see, I will mainly focus on one technology, which is the floating offshore wind. Just a slide on Bureau Veritas. We have been working on more than 90 different offshore wind projects, so both fixed and floating, that represent globally an installed capacity of 25 gigawatts. And we have a network of 340 professionals, so it's mainly surveyors and engineers working on this domain. Just to understand the certification context, I think it's interesting to have a look at the key trends of the floating wind industry. So first of all, this is an industry which is transforming. As Flavia and others explained, we're transitioning from prototyping to commercial projects, also including newcomers like the international oil companies, Total, BP, and Shell, for instance. This industry is also very quickly expanding. So we are talking about a two-digit growth of this market in new regions like Brazil. And it's still innovating a lot. As you may know, there are roughly 40 to 50 different floaters concepts on the market, of course, at different TRL levels. And also new materials, or at least new usage of existing components or materials. I can mention, for instance, the synthetic fiber ropes made of polyester or nylon, and also the high voltage dynamic cables. So analyzing these key trends, there are 3 main challenges, which are how to mitigate the risks of such projects. Second will be to know if the supply chain will be ready to deliver on time and at the quality level expected. And also how to select the most suitable technology for a given project. So considering all these challenges, certification is a way to address them. So in this section, I will give you more details about the certification of marine renewable energies. First of all, you have to know that in most of the cases, the certification is not mandatory. It means that it's not imposed by the local authority. On the other hand, it will be usually strongly recommended or even imposed by different stakeholders, typically the insurance companies. There are several types of certification. the first one I will describe is the approval in principle and also the prototype certification. So that's typically addressed to technology developers and designers in aiming at enabling the go-to-market of new technologies. After that, we can also provide project certification. So here it's mainly addressed to project developers or operators with the objective to de-risk the projects and improve its safety and its quality. If we are performing certification of floating wind projects, because the certification body is in a unique position to de-risk the project. Let me explain on that. The typical setup of floating wind projects involves many different actors. You have the project developer, then you have the turbine OEM, you have also the floater designer, and even the dynamic cable designer. So you have a lot of interfaces between all these different actors, and obviously they have to exchange some information for designing their components, but it's limited due to IP or confidentiality. On the other hand, the certification body is in a unique position to gather all the different information coming from the different designers, for instance, the turbine controller, because we'll have to build our own independent model, complete model of the wind turbine, so including the turbine, the floater, the mooring system, everything, such as to verify the wind turbine, the loads in the wind turbine. So it's very important to have a certification body on board as a third party, having a look on the entire project. So talking about certification, indeed, this is an exercise of conformity assessment to technical standards. So indeed, the certification schemes or procedures are explained in some guidelines. For instance, the IEC RE for renewable energy OD 502, or equivalently in the BV guidelines NY 631. So here you will find the different certification schemes, the input, the output, and also the process will be described. And as I say, then it will refer to technical standards. So coming back to this example of floating wind applications, technical standards applicable most of the time to the turbine and the tower will be the one published by the IEC TC88 working groups. And so that's the 61400 series. And for what concerns the floater and the mooring system, usually here we'll refer to the classification society's rules. So for instance, the BVNY 572, what concerns the floating wind projects. So just a few words on these technical standards. So the NY 572 will give you technical requirements to be addressed by the designers all along the project lifecycle. So if we focus on the design phase, you will find requirements on the materials, the design conditions, the load cases to be considered, but also requirements in terms of stability, structure design, so strength and fatigue, and also marine, that also covers marine systems. We've also published equivalent guidelines for current and tidal turbines. So that's the BVNY 603. So coming back to the different certification schemes, there are several depending on the type of project, the maturity of the projects. So I've mentioned the approval in principle, which is a concept pre-certification. After that, we can also perform the prototype certification, which is very close to the full project certification. But as the operations of the prototype will be limited in time, so typically during a period of 3 to 5 years, the design requirements will be a bit less stringent as compared to full project certification. And the other difference between prototype and project certification is that a prototype usually will be instrumented. So it means that in terms of certification, we will review the instrument and test plan, which will be provided by the designer. So the next schemes are the component and type certification. So typically for offshore wind projects, the blades are component certified, and then the full RNA, rotor nacelle assembly, the wind turbine, will be covered by a type certificate. So the type certification is not specific to one project. It's covering different types of project, many applications. So it means that in the context of the full certification, or real project certification, we will not evaluate again all the internal components of the turbine, but we will just evaluate the validity of the type certificates. I will come back to that point. Let me give you a bit more details on the approval in principle. So as I said, it's kind of concept certification, so addressed to designers. And the main objectives here will be to establish the design codes to comply with. So for offshore wind, it's obvious because technical standards are already available. But if I consider emerging technologies like floating solar, for instance, it's not an easy task to find appropriate technical standards. So here we have to benchmark the existing design codes and sometimes adjust some requirements to address one specific technology. The next objective of the AIP will be to verify that the design is feasible, achievable, and contains no technological showstoppers that may prevent the design from being mature. So here it's important, it's kind of de-risking of the technology. And at the end, the certification body will issue comments and recommendations to be addressed during the further steps of development. It's because at AIP level, usually the designer cannot consider all the different comments, but let's say the concept will at the end be a prototype, then some additional comments or recommendations will have to be addressed. For what concerns new technology, sometimes it's not possible to certify it as is, and before certifying this new technology, we have to qualify it. So at BV, we have developed guidelines for the qualification of new technology, which are based on risk considerations. So typically, we will perform HAZID, HAZOP, and FMECA, failure mode effects and criticality analysis, such as to be able to qualify the new product, new technology. After what we'll be able to certify it. So now let me give you a bit more details on the project certification. So as I said, when we'll have to perform the project certification, we will consider the type and component certification which have been performed. So it means that we will evaluate on the validity of the type certificates. So this project certification scheme that you can see on the right-hand side of the slide is made of independent modules that are evaluated by the certification body one by one. And for each module of the certification, we will issue two deliverables, a conformity statement for this module and an evaluation report. And if we have to just explain the different phases, you have a first step, which is the certification of the design phase, covering the site condition assessment, the design basis, the loads, and the detailed design. After which we will certify the manufacturing phase, the transportation installation, and the commissioning. So once we have evaluated properly the different mandatory modules, we'll be able to issue the final project certificate. As options, you may include different modules. So there is one named Other Installations. So typically, this module will cover the entire cables of the offshore substation, if any. The project characteristic measurements also can be evaluated by the certification body. So that's typically the certification of the power curve. And the operations also can be included in the certification. So traditionally, in most of the cases, the certification will not be maintained during the operations, but it's possible. So very quickly, I will go through all these modules. So the first one is site condition assessment. So here, the key question is to know if the assessment is adequately undertaken by the designer and well documented. So here I refer to the Meteocean condition, the wind characteristics, regular wind and turbulence, and also the geosciences aspect. Next is the design basis evaluation. So here it's not only one document, but it's several design bases. So the part A, which is produced by the project developer and mainly addressing the site environmental conditions. Design basis part B covers the wind turbine and the tower. So that's obviously produced by the turbine OEM. Part C will cover the foundation, fixed or floating, and including the mooring system if it's a floating foundation. And part D is for the other items like the inter-array cables. So here, as a certification body, we'll just make sure that the different technical standards and norms used by the designers are coherent at the interfaces, so between the turbine OEM and the floater designers, for instance, and that there is no gap in terms of technical standards. Another thing that will be carefully checked by the certification body is the design methodologies. So at this stage, we will review the load cases, we'll review the fatigue methodology, the load analysis as well. So all the different project methodologies will be evaluated. Third important point is the integrated load analysis. So here it's very important because, as you may know, for floating wind projects, there are a lot of different couplings, notably this coupling between the wind loads and the hydrodynamic loads. So the certification body will have to build its own independent model. So this is, as I explained before, gathering all the information coming from the turbine OEM, the floater designer, such as to evaluate the loads in any point of the structure. So once we have computed and verified the site-specific loads, we'll be able to compare these maximum loads that you will find on the site with the allowable range of loads as specified on the type certificates, such as to validate or not the type certificate of the wind turbine. So let's say that you have validated the type certificate. It means that in terms of detailed design evaluation of the wind turbine, you don't have to do much because it's already covered by the type certificates. On the other hand, you'll have to analyze carefully all the site-specific components. So that's the tower, which is designed for, let's say, optimized for each site, the foundation, floating foundation and the mooring system, and the inter-array cables, if covered by the certification. So during this design evaluation module, we will make sure that the methodologies that were described in the different design bases are properly applied by the designers. And in parallel, we'll also perform independent analysis to validate the results of the analysis performed by the designers. So the next steps are about manufacturing, transportation, installation, and commissioning. So here there are two main activities. The first one is the documentation review. So we will review the quality system of the different sites, just to make sure that the manufacturing site is certified according to ISO 9001. We'll also make sure that the different welders and NDT operators are qualified to perform their jobs. After that, we will also perform regular inspections, such as to evaluate the base materials. So we'll review the steel or different materials certificates. And we'll also witness the different assemblies that are produced by the manufacturing places. So we'll carefully review the different welds, the tolerances in terms of misalignments, etc. During the T&I phases, we'll act in parallel to the marine warranty surveyor, which is another third party acting during the same phase, but looking at different things. So here, we'll just make sure that the transportation and installation procedures are in conformity with the methodologies that are described in the different design bases. So that's the primary objective. So once we have validated all these different modules that I've explained, we'll be able to issue the final project certificate. After that, we could also certify the OEM, so the in-service phase, performing regular inspections, periodic inspections that are based or not on RBI, risk-based inspection regime, and agreed with all the parties involved. So that's it for me for this overview of the project certification. Don't hesitate if you have any question. I can take a couple of them, I think.
Thank you very much, Jonathan, for the nice and instructive presentation. Certification is surely one very important topic in our discussion today. We have one question I think we have time for one question. I have one from the audience, from Ingrid Silveira. I don't know if you can answer on that, because it's related to wind measurements. She says, what is usually the certification procedure for offshore wind resource measurements? Is there a common understanding about the best practice for this procedure? For example, LiDAR measurements or onshore met masts?
Yeah, so usually a floating LiDAR will be deployed on site. So I think that's maybe the best option and most accurate option. If you want also to optimize the design, I mean, the first step will be to evaluate properly the environmental conditions, because we know from experience that it has a very strong impact indeed on the design. Just maybe the wind turbulences, for instance, may have an impact on the fatigue performance of the mooring system in some cases. So I think it's very important to evaluate properly the site conditions.
Okay, thank you very much. We have to move to our next presentation. Thank you again, Jonathan.
Welcome.
We have, now we have actually two presentations from the National Renewable Energy Laboratory in the United States. The first one will be presented by Nathan Tom. Nathan joined NREL in May 2014 after receiving his PhD from UC Berkeley. While at NREL, Nathan has been on several international projects, which include WEC and the Wave Energy Converter Control Competition. Currently, Nathan is the principal investigator on a project that explores the concept of controllable geometries for wave energy converters. Nathan is a subject matter expert in the IEC TC114, supporting standards development for marine energy devices. In addition to technical work, Nathan assists in the development of educational material to support the future marine energy workforce. Well, thank you for joining us today, Nathan. Please, the screen is yours.
Thank you for that introduction, and thank you for the opportunity to speak this morning or afternoon, depending on where you are. And just confirming that everyone can see my presentation.
Yes, we can.
Awesome, great. So as mentioned, my name is Nathan Tom, and I'm a staff researcher at the National Renewable Energy Laboratories. And the National Renewable Energy Laboratory is a federally funded laboratory as part of the US Department of Energy, Water Powers, Technologies Office. And so I'm going to focus my work or my presentation today on the types of research and development that we are pursuing in the United States to commercialize the technology. So as mentioned, as a federally funded lab, we get a lot of funding and support from the US Department of Energy's Water Power Technologies Office, which is where any development in marine energy systems fall. And to give you a little bit of a background on the US DOE WPTO, so the Water Power Technologies Office, one arm is marine energy, and marine energy, they're looking at utility scale and also on blue economy scale. So looking at different application areas for marine renewable energies, but also looking at run-of-river and conventional hydropower. And those are kind of all the kind of technology areas that WPTO looks at. Also helping to, and I believe was already kind of shown on the first speaker, but helping to look at evaluating environmental impacts of marine energy and traditional run-of-river systems on the environment. So why we need the funding and we need support from the WPTO, and I can expect that everyone on this presentation is a naval architecture familiar with working in the water, but we know that working in the offshore environment is difficult. At least for marine renewable energies right now, we have a fairly prolonged design and testing cycle of taking something from paper, getting it to a sub prototype in a wave tank to getting it to a smaller pre-commercial offshore and just going up all the way to a larger WEC array or marine energy system array. Work, as Rhoda mentioned, a difficult engineering concept. It's also very difficult and challenging to install and operate systems offshore. As shown in the picture, biogrowth, maintaining systems offshore is not easy and not cheap. And also, given that marine energy is one of the more, let's say, younger of the renewable energy technologies, we don't quite have maybe the market information supply chains that are needed to drive the cost down that is needed to be competitive with other renewable energy technologies. And so in response, what the history of the Water Power Technologies Office has been compared to some of the other renewable energy technology programs funded by the US Department of Energy, such as solar and wind, the marine energy group is much younger. There was not really an official program established until 2008. And at that time, it was mostly getting a program established within the United States, establishing a set of national marine renewable energy centers, which consists of different universities in the US that focus on the application of marine engineering, specifically on marine renewables, and also establishing several federally funded laboratories to do work in this field, which includes NREL, the Pacific Northwest National Laboratories, as well as Sandia National Laboratories. And so since 2008 to now, there's been several major projects and efforts done, starting off by giving funding to industry to start to develop concepts so that we have that, as mentioned on the previous slide, that really long design timeline, getting developers working to get prototypes in the water, doing resource assessments on the US and all of the contiguous islands, starting to do reference models of trying to see where we are. Reference model project I'll discuss a little bit later, but kind of benchmarking state of the art earlier in the 2010s. And then in the last couple of years, some major things that have been run are prizes such as the Wave Energy Prize, trying to help promote innovation. We have a large grant to develop one of our largest grid connected testing facilities offshore in Oregon. We've established a little bit, and I'll talk about that more, Teamer, making it easier for industry and academics to access testing infrastructure, as well as introducing the Marine Energy Collegiate Competition. We're just hoping to help train the new workforce that will be needed as we see marine renewable energy and the blue economy the industry is supporting the blue economy as we expect them to grow in the next several years. And so this is just a slide to illustrate what the marine renewable energy resource is within, around the United States, and why there's interest from the US Department of Energy. And on this graphic here, we're showing resources from wave, tidal, ocean current, ocean thermal, and run-of-river. And you can see very quickly from the pie charts that wave energy is definitely the dominant marine renewable energy resource in the United States. That's followed by tidal. OTEC is there, but it's definitely focused on some of the island nations that are part of, island territories that also comprise the United States. So a lot of energy and effort goes into marine renewable energy and tidal energy. Ocean current, we have one large resource off of the Florida, and that's kind of where the only location you might be able to extract ocean current economically. So I touched upon it before, but what the US Department of Energy did early in 2010s, I believe all these reports were published around 2014, 2015, was to do a more detailed design on 3 tidal, current, or run-of-river systems and 3 wave energy converter systems. And I put a link in here, which you're happy to look at and get various reports and understand the detailed technical analysis completed. But this was to benchmark where the cost of energy stood, again, about 2014, 2015 for these different type of devices, which you would commonly see if you did like a literature search. And this would help us understand how much we thought marine energy systems would cost, and then understand where do we need to target research efforts to make them more cost competitive moving forward. Okay. So in addition to this, WPTO has worked to establish other open ocean testing berths to allow developers to slowly move from their concept to a more sheltered bay before going to some of the larger, more energetic seas. And one of these locations is off of Hawaii, and it's called the Wave Energy Test Site off of Oahu. And we have an aerial view of where this testing berth, which includes 3 different testing berths, where it's located. And then the pictures on the right are some of the developers that have been testing there, or will be testing very shortly. That includes the Northwest Energy Innovations Azura device, which is a hybrid heaving point absorber concept. You have the Fred Olson Lifesaver on the bottom right, which is a ring, essentially hole that's tension connected to the seabed through 3 tethers, which are then connected to a power takeoff or generator system. And then one of the largest devices that is going to be tested, and is, I believe right now in dry dock, or at least its berth in Hawaii right now, is the Ocean Energy OE35 oscillating water column. And then that is kind of where a lot of our developers go to do kind of their first testing. It's the first time in the water with a fairly large device. But as mentioned in one of the previous slides, WPTO has made a significant investment in establishing PacWave, which is the goal is to have it grid connected and being able to handle WEC arrays. So you're talking about 5 megawatt devices or arrays, and a lot of investment and time is going into getting this up and running, and it's expected to come online sometime around, I think, 2023 to 2024. But this is definitely a pre-commercial site. We are going off the coast of Oregon, has one of the best resources in the United States. So definitely, if you're a developer coming here, you want to have your prototype or concept fleshed out a little bit more from numerical studies, wave tank tests, and again, testing some of the other offshore sites that are less energetic. So all that's been focused a lot on what WPTO has been doing in terms of utility scale power, and already mentioned by several previous presenters, but there's also a new research focus on looking at using rain energy to power the blue economy or find other opportunities offshore that marine energy can fit powering needs. And this is pulled from a report that was published by WPTO and NREL and other laboratories, highlighting some of the key areas that we think marine energy can play a significant role in providing a power source offshore. So we have power at sea, which includes ocean observations, underwater vehicle charging, marine aquaculture, marine algae, potentially seawater mining. And we also have another area where it's the resilient coastal communities. This includes desalination, disaster recovery and resilience, and also supporting isolated communities that might be very far away from a conventional grid. And so a few active projects we have supporting the powering the blue economy. One of these projects that I really like is the Igiugig, Alaska ORPC RivGen project. And ORPC is a run-of-river or tidal energy converter. And you can kind of see their design in the bottom right that's being deployed in the river. It's a cross-flow turbine, but ORPC is trying to support this remote community in Alaska. And you have in the upper left corner a lot of the tribal community in this village. And it's a really good case study of ORPC had spent a lot of time with the community figuring out what they needed. It's easy to say that we want to transition this community off of diesel, but it's very important to figure out what they need. They want to make sure that the lights are always on, and they also are very conscious of the environmental impacts because it has a very large salmon run through their village, which is what they need to survive. And so it was just a really good, I think, case study of how, as engineers, we need to go into a community, make sure that whatever we are designing is going to fit what the community needs, because if not, then they won't ever adopt it. We also are looking at supporting some of these research efforts through prizes. So one of these is the Department of Energy's Wives to Water Prize. And this is looking at trying to develop cost-effective desalination systems that are powered by renewable energy systems. This prize is a little bit also looking at trying to find designs that can support the disaster recovery. So one of the key features of this prize is that any concept that anyone is proposing would need to be set up within 48 hours. So it's something that you could, right now we have in the Gulf Coast of the United States a lot of hurricanes. So if some kind of disaster like that came through, you could have these deployed very quickly to provide fresh water and also electricity while the larger infrastructure comes back in to be fixed, like larger trucks and other types of tools you need for that. We also have another prize, which is the Ocean Observing Prize, which is looking to focus on that ocean observing. So we're looking to try to find systems that can, for part of the day, collect information, salinity, temperature, GPS, maybe it's tracking a school of fish or something like that. And then half the time, be able to charge itself so it can continue to operate offshore without having anyone need to come and recover, dispose of batteries. And so this is a joint operation between WPTO and the National Oceanic and Atmospheric Administration, another US entity. And then again, we have a lot of work now too, looking at trying to not only establish a workforce potentially to serve all sorts of marine energy applications, but offshore applications. And so WPTO set up the Marine Energy Collegiate Competition, where collegiate teams have the task of trying to come up with a marine renewable energy design and then couple it with a powering the blue economy market. So they might be trying to develop a desal system. We had someone like that last year using marine energy to pick up plastic or trash in the ocean. So we're trying to have them think about other ways that you can use marine renewable energies to serve different communities or basically different applications offshore. And mentioned a little bit by the previous presenter, but also a large part of WPTO strategy is to have both academics and national lab researchers participate in the IEC's TC114, which is the Marine Energy Standards Development for Marine Renewable Energy Technologies. And so we partner along with a lot of other nations participating in IEC, and it's very helpful to collaborate with all the experts around the world to try and figure out how we can evaluate designs uniformly. And then we also have, as I mentioned before, recently started to set up an infrastructure that gives access to industry and academics within the United States, and actually internationally. You can apply to our Teamer program, which gives you access to testing and numerical modeling expertise. So you wouldn't have to have a concept or something you want to try out that's already been built. But if you need to go to a larger wave tank, you're trying to test out a larger generator system, we have facilities within the United States. You can apply for money to get the support to test, not necessarily design your system, but to test it and see what improvements need to be made before moving on in your own design cycle. And then another large part of, as a government agency, we're trying to do is collect and organize the massive amount of information that is available both within the United States and internationally. So we have 3 different large data repositories, TETHIS, which is a focus on kind of environmental monitoring and data, TETHIS Engineering, which is focused on more the engineering design, technical papers, and then Primer is another hub where we store our current science, technology, education material, and some other auxiliary information. But all of these are trying to help coordinate the marine renewable energy industry, both within the United States and globally. So thank you again for your time. I think I ran a little bit over, but happy to try and answer any questions anyone has.
That was perfect, Nathan. Thank you. Thank you for sharing with us all this important work that is done by NREL to promote marine renewable energy. We have time for at least a question. I see no question here in the Q&A, but I have a question I'd like to discuss with you briefly. Regarding, we have been discussing here in the university for some time the necessities and the opportunities for a marine energy hub, or something like you presented in one of your slides, for providing power to mostly, for example, for monitoring activities, right? For environmental monitoring, ocean monitoring in general. Can you tell us how do you see, or what's your expectation in terms of these kind of project going ahead and actually becoming concrete, and how do you see the economics of that? Because it seems something really important at this moment, right?
Sure, and I'll definitely try to answer my best. I definitely think that there's a lot of opportunity. As part of the Powering the Blue Economy report, there was a survey of a lot of offshore, not just marine renewable energy industry members, but anyone that works in the offshore space. And they did an analysis of kind of the power requirements and needs for offshore monitoring. And it was very clear that if you could build a system that was able to produce power reliably, then you'd have a lot of customers right away. NOAA is an organization in the US that already kind of said, yeah, if you could give us, between 10 and maybe 500 watts, they don't need necessarily kilowatt or megawatts to run their monitoring systems. They would immediately want to invest in that, rather than have currently what they have to do is deploy something, go out and retrieve it. So I'm not an my expertise is not in economics, but the work that they've done shows that it's one area where there's definitely already like a customer that if we can make a reliable device, they'd be willing to purchase it. So I do think it's a good opportunity moving forward.
Okay, thank you. Thank you very much, Nathan. I will move to the next presentation from our colleague, Energia. I have a second presentation from the National Renewable Energy Laboratory. This one will be presented by Senu Sirnivas. I hope I got that right, Senu.
Yes, you got it right. That's good.
Okay. Senu is responsible for leading and executing research programs to address emerging issues in the development of offshore wind energy technology. He advises, facilitates, and executes laboratory initiatives in offshore wind and marine hydrokinetics, working closely with the US Department of Energy, with the industry and university research partners. Prior to joining NRL, Senu worked in the offshore oil and gas industry for 20 years. Starting at Deep Oil Technology, the original Spar technology company, he has transitioned through Aker Maritime, Coflexip, and Technique. Prior to leaving Technique, he was the head of the floater product line software development group. In his last position at Horton Wisen Deepwater, he led the efforts on offshore floating wind business development. So we'll now have a speech from NRL on offshore wind. That's very nice. Please, Senu, go ahead.
Thank you, Alexander. Can you guys hear me? And I'm going to share my screens and let me know if you can see.
We can hear you. We cannot see your screen yet. But...
Sure. You see the screen?
It's coming. Yes. Now we see a frog. Yeah.
Yes. You see a frog, or you see a presentation?
Now your presentation is fine.
Okay. All right. So I think Nathan did a great job, talking about NREL a little bit and how we are related to DOE. I know that we're probably running a little short on time, correct? So I'll try to speed this up so that the next presenter will have some time. So as Alexander said, I'm Senu Sirnivas, and I've been here at NREL now for 10 years, and I've most of my background has been in engineering in oil and gas, designing floating systems. And so I'm here helping Enroll with offshore floating wind, but also with fixed bottoms as well in marine hydrokinetics. You move on to the next slide here. I just quickly wanted to give you guys a background. I know Nathan talked about Enroll and how we're related to the Department of Energy. But just to give you a brief history of where Enroll started, it started as a solar research institute in 1977. And then in 1991, it was designated as a national lab. And in the process, a lot of the national labs are being run by private entities, and Enroll is being run by Alliance of Sustainable Energy, which is a private entity that manages the lab for the Department of Energy. Moving on to the next slide here. So what I wanted to quickly also address is, Enroll is, we work on water power, we work on wind, but it's bigger than that, right? We have a world-class facility that addresses a lot of different things in the renewable space. And Enroll is the only national lab in the US, a part of the Department of Energy that is totally dedicated to renewable energies, from biofuels to solar to energy efficiency, buildings and whatnot. So it's bigger than just water power or wind. And to date, I think we have about 1,700 employees at the campus, and there are really two parts of the campus. There's one in Golden that houses all the energy efficiency and grid integration and stuff over there, and then we have the wind center, which has Nathan and myself in it as well. And we get a lot of international collaboration, mainly from Europe and other parts of the world, where we have researchers coming in to the lab, to do internship, for 3 months, 6 months. And so there's a lot of collaboration that goes on internationally with the lab as well. And one other thing I want to mention is, we also have a lot of industry collaboration, not just with academics, but also industry as well, right? Like GE and Siemens and so on and so forth on the wind side. And as Nathan mentioned, we work with a lot of the water power folks as well. So I just quickly wanted to show you a picture of the campus itself. This is the wind side. This is not the main Golden campus. And this is really a campus where we actually have wind turbines at site, and we instrument them, we test them, and we have very solid winds, extreme winds coming down from the other side of the mountains, and we can get up to 80 miles an hour wind, hurricane level winds. At the site, and sometimes the wind center closes down because we're not allowed to go in there because the winds are just too extreme. And we instrument the blades. We have met towers there to measure the wind and see what happens to the blades and so on and so forth. We have a testing center for a structural testing center where we can test the blades until it cracks and do fatigue testing on it. We have a dyno, and what's next on the list here is to have a control center, power control center that can integrate, power centers, power coming from solar, from wind, from different sources, and how do we control it in the grid. So that's next on the list here, and that's not shown here on this picture. Moving on, I quickly want to address why floating offshore wind, at least in the U.S., right? And the recent administration, at least the Biden administration, has put a big focus in climate change, and also a big focus in offshore wind. And it's been talked about quite widely here. And the only way we can get to what the government needs to for wind electricity, to get to 35% of wind electricity, is to go to offshore wind, because the land-based wind is pretty much occupies a lot of the mid part of the U.S. and there's still space there for that to happen, but we cannot get to 35% U.S. wind electricity without going to offshore wind. So I just quickly want to illustrate that. And if you look at this chart, you would see that, fixed bottom is about 42%. That's about 32 gigawatts. And, that's when I say fixed, I'm talking about less than 60 meters. And then floating is above 60 meters, we're at 58%, right? That's about 50 gigawatts, right? And you can see in this graph here, the land-based cost is going down, but it's become pretty flat down here. The offshore wind cost is slowly going down, And in the long run, given the higher capacity and bigger wind turbines, we feel that we can pretty much match what the land-based wind cost is going to be here in the U.S. So moving on to the next slide here, I just quickly wanted to show you the resource that we have here in the U.S. And in this map, you would see the darker blue, which would be the floating wind, and the lighter blue will be fixed bottoms. This will be jackets, monopiles, etc. Right? So if you look at the blue one, and you can see it's mostly in California. I mean, California up here, and it's on the West Coast. And a lot of the deep water ones for floating is also a little bit further out in the East Coast. But you can see the first projects that are probably going to go underwater in the water is going to be fixed bottom. There's already one which is in Rhode Island that's been operating 5 turbines out there, 6 megawatt each, I think, and that's fixed bottom, and that's in Rhode Island. And there's a lot of leases that's been awarded in the New York area and New Jersey area. There are leases that are being planned right now for California as well. And also there's also very deep waters in Hawaii as well, right? So if you look at the US, we're behind in terms of deployment compared to Europe. Europe is just way ahead in the game, but from our side, we have to compete with other resources, energy resources. Even though they're not renewable, we have to compete with them, and we have to have a market for them. And I'll talk about that in a little bit here. So moving on to the next slide here, what was the, to just quickly address, what was the problem with floating wind to start with? One of the problems we had with floating wind is, we are borrowing a lot of technology from oil and gas, right? And I come from this industry, and we always build one-off things. We don't mass produce them. We build one-off things for a specific site. So we have taken this oil and gas technology, and then now we have floating offshore wind, for jackets or monopiles or whatever. They're all really borrowed from oil and gas. And one of the things that I wanted to say was, I think there are better ways to maybe design floating wind technologies, or even jacketed structures for offshore purposes, and to bring the LCOE down, to make it competitive with other sources of energy. And one of the things I wanted to say is, at least in the US here, there's been a big push from the Department of Energy, particularly ARPA-E, recently. Last year had an award for 5 different Area 1 projects that were looking at innovative structures, right, for floating platform. And the idea here is to build the system integrated, right? I mean, to look at the system integrated. And what I mean by that is, you're not just going to do a decoupled analysis of, getting information from the turbine manufacturer and then uncoupled, doing a simulation with the floater itself. What ARPA-E wants to do is, they want to do what's called a control code design. How does the whole system react, and how we can optimize the entire system? That includes the turbine, the tower, the platform, the mooring system, anchors, and so on, right? And so their target for ARPA-E was 7.5 cents a kilowatt hour. That was the target, right? So a lot of different, like I said, there are 5 different participants, and they're all trying to get to 7.5 cents a kilowatt hour. And this would be a little bit more expensive than land-based wind, but we're getting there. I just wanted to mention that real quick. And the other thing is that's important for wind, and I think this is true everywhere, and particularly here in the U.S., is collaboration. So one of the things I want to say, a lot of the tools that NREL has is open source. You can go download them, you can use them, and you can go into the forums and ask questions. So we have these advanced tools that we have at NREL here. We work with standards, we work with theory, and innovations, like for example, that's coming out of ARPA-E, and we're modifying a lot of our codes to adapt to the innovations that's coming out of the Area 1 teams there. And we are making our engineering tools so we can look at advanced wind technology, right? We have test data that we also, and we have a computational center here with high fidelity modeling, where we have a HPC center that allows us to run very large simulations in computational fluid dynamics as well. So we incorporate all this, and then we have the advanced wind technology. And now what we want to do is, the labs can't just isolate themselves and work by themselves. We have to work with industry. If you look at the wind industry is ahead of the water power industry in the sense that there is there's a commercial applications for the turbines and whatnot. So they are way ahead. And how do the labs such as NREL and other labs work with industry to actually advance the solution, right? So in this space, we're looking at a lot of different things. We're looking at new actuations, advanced sensors, definitely a lot of CFD solutions on how to do wind plant control and not just control of individual turbines, right? And the bigger thing for at least from my end is, we have advanced tools. Yes, we want to work with industry that's OEMs, building wind turbines and looking at technologies like PPI and so on and so forth. We also want to work with the developers like Exxons and Chevrons and Equinors, because without the energy companies being involved, we really can't make this happen in the US. So there's a big push from at least myself to get integrated with the energy companies, the developers, who are actually going to produce the energy and supply to the market. Yeah, so that is the next step that we're working on here at NREL. So I quickly wanted to go through the three challenges that we're trying to address, and there's a paper out here. Out there that you can go take a look. It's a very good paper, quite thorough, and talks about all the different challenge areas that we need to address, going forward in the wind industry. One, of course, is to understand the atmospheric physics, the flow physics, that is still evolving, right? And we're doing a lot of the work here at NREL, looking at meso-micro coupling of larger simulations to smaller simulations, and so on and so forth. And then you have, of course, how does the platform react? What are the aerodynamics, the structural mechanics of the system itself? And then you have the grid integration. How does the wind system integrate to the power grid, right? Because wind is not always going to be there. We have to balance it with other sources of energy. And how do we do that? So that's another big area of research here at NREL. I quickly wanted to go over the open source tools because I talked about this, and as I said, anyone can go download all the tools that we have, and you can use it. And a lot of the academics use it, and industry use it as well. And we have different model fidelity, right? For example, at an early stage when you're looking at something, you want to do something really quick. You could use something like Forest, for example, to do wind plant control optimization, etc. Right now, if you want loads on the wind turbines and so on, then maybe you want to move on to OpenFast or FastFarm. OpenFast is a single turbine, but you can definitely use FastFarm, which is OpenFast simulation, but you have multiple turbines, right? And you can get loads from the turbines, and then you can do your design analysis. Now, when you talk about looking at the atmospheric interaction, the flow physics with wind turbines, then you want to go to maybe a high fidelity modeling tool like SOFA and ExaWind, where you can really do blade resolves and things like that. Now, of course, this comes with a computational expense, right? You need a big high performance computing center to run simulations like this. But these are the kind of things that we're doing to try to address the three research areas that I talked about earlier. And as I just wanted to point out again, these are all open source. You can go download them and you can use them. Now, I'm just quickly going to go through some of these tool sets that I mentioned, and I'm going to go through them quickly. So this is the OpenFast tool. If you look at the OpenFast tool, this is really the core for a lot of the research that we do. And this builds into a lot of the other tools we have. And if you look at the OpenFast module, we have the inflow, we have Aerodyne, Hydrodyne. These are all different things that do different things, but they're all modular. And they come together, and you can do a simulation of the entire floating wind turbine or fixed bottom in real time, right? And you can run the IEC load cases and so on and so forth. And there's also linearization, because linearization is important for us to understand how the system reacts, so we can build controls around it, right? So that's another big big reason why we use OpenFast, and we have the ability to really look at the system as a whole. Now, the next one here that I want to talk about is Forest. Now, this is the very low end. You can run this on laptops and whatnot, and you can run the entire wind farm, right? And you can actually do a wind farm layout. Let's say, for example, you have an area you want to develop and you want to say, hey, you know, where do I really need to place my wind turbines? You can use Flores and you can say, okay, you know, try to optimize the layout to produce the maximum power production, right? And you can also implement wind farm control, not individual turbine controls, but you can control the wind farm. Right, maybe you want the front turbines to produce less power, so the turbines in the back can produce more power. So overall, in the wind farm, you can produce more power and as a collective. Going on to the next slide here, this is fast farm, and the animation that you see here is just for a single turbine. But what you can do here is you can have multiple turbines, and we have done simulations up to 100 turbines. In fast farm, and we look at, you know, how the wake between the wake in the front turbines affect the turbines in the back and power production, and we can also change the controls and also change the angles that the blades are angled to, so that we can produce more overall in fast farm. This is just a higher fidelity model compared to Flores. Flores, you want to use it to do wind farm layout and things like that, and maybe some optimization of where the turbines should be placed. And then you can go to fast farm, which is, you know, which will be your next level, where you're looking at more details and trying to get loads from the blades and the platform and whatnot, so you can do more design work on it. So going on to the next one here. Let's see. It's kind of stuck. Oh, there you go. I think I moved too quick. All right, so the next one here is, of course, a high fidelity modeling, right? We talked about, you know, Flores, which is very low fidelity. You can do quickly. You can look at lots of cases. Then you can run it in fast farm, which is higher fidelity modeling. And then you can really go to very high fidelity modeling, where you can look at the wind park. And I think this is a wind park in Denmark, and where you can see the flow going through the system, and you can see the wakes and being generated and so on and so forth. And down there, you can see how the simulation actually replicates some of the measurements that were made there at the time. I'm going to go to the next slide here. I know we're running out of time. So this one is an interesting one, is because you know, I talked about this earlier, where we want to do wind farm control and how we want to change the angle of the front turbine so that we can produce more power on the back turbine. And you can see the power difference. You know, if we don't do any yaw alignment with control of the turbines, and we do yaw misalignment, so we can direct the wake differently, we can actually overall produce more power. So this is some of the high fidelity work that we're doing and research we're doing here at NREL. And I think that was my last slide. I think I am on time, and I'm open to answer any questions. I know I went through it really quick. But I'm open to address any questions that you guys might have. I really want to thank the team for letting me present here and letting us, Nathan and myself, present NREL and the kind of research we're doing here. I really thank you.
It's certainly our pleasure to have you here, you and Nathan. I understand it's also early in the morning for you where you are, I think, right now. So thank you guys for joining. We're on time, as you said, but I really appreciate that you ran through your presentation. We have been working on floating wind projects here academically in the university. We know OpenFast and Flores, we've been using it. It's important tools for us, no doubt about it. I just have a very small, quick question, Senu, regarding one comment that you made on optimizing the floating wind concepts, which of course is crucial for competitiveness. But I believe, as you know, you told us you have a big project on that going on right now. From our side, from our perspective, from the academic perspective, I think there is a lot of potential for optimizing these structures, but it's critical that we have the turbine manufacturers joining in. Do you have them joining in this effort for
Yes. So what I was talking about was ARPA-E Atlantis, which is a control co-design. And I mentioned, I think we have like 5 awards. And some of the awards are actually collaborations between GE and Glaston, for example, is a collaboration where they're looking at TLP. So you have the turbine manufacturer involved in it. There is also PPI has an award, but it was not in Area 1. There are some academics like University of Maine, for example. You know, I think they're working with Siemens. I'm not really 100% sure, but there is some collaboration between turbine manufacturers and platform designers. And I know it's a big problem, at least here at NREL. Getting control information to work with turbine manufacturers is very, very difficult because it's proprietary to their turbine, and also you know, the blade profiles and whatnot. And it makes it very difficult to do a control co-design, right, without the turbine manufacturer being on board, because it's always done sequentially. You know, they give you information, then you do your stuff, and you can't really do a complete optimization. But there is some level of collaboration, at least in ARPA-E there is, because the industry is involved in it. There is a project that I'm running, which is also ARPA-E, that we don't have a turbine manufacturer involved in it. We're just using a generic turbine, like, you know, you can say now you have the IEA 15 megawatt machine out there, and there's a DTU 10 megawatt. At least in the one that I'm running right now, it's a DTU 10 megawatt, and we're doing a control co-design with a DTU 10 megawatt machine, which has details about the, you know, blades and whatnot and so forth. So it's a gap that we have to bridge going forward, working with the turbine manufacturers. That's why I was saying, and I was trying to tell everyone that we cannot get there without the industry being involved, and at the back end of it, you need to have, you know, the energy companies involved as well, because eventually you're to sell the product. So you have a very good point, and it is something that we struggle with all the time.
Okay, thank you very much, Senor. I don't know if Milad, do you have any comment? No. Okay, we have to thank you very much once again, Senor. Nice presentation.
Thank you. Right.
Thank you. We'll move on to our final speaker, a final presentation in our event today, which will be given by Carlos Leandro from OceanPact. Carlos has a bachelor in oceanography from the State University of Rio de Janeiro, and a master in remote sensing applied to oceanography from the Brazilian National Institute for Space Research, which is INPE. Regarding his professional experience, he was a university level specialist in the hydrobiology laboratory of the Federal University of Maranhão. Then between 1989 and 1996, he worked as an employee in the remote sensing division of INPE. Then he moved on, and from 1997 to 2003, he was the CEO of OceanSat, Space Technology for Environmental Monitoring, and marketing director of OceanSat also. And finally, between 2006 and 2018, he was a partner director of Petro Survey and Innovation. Currently, he's coordinating the Kronos project, which is a platform that integrates meteoceanographic data from different sources at OceanPact Maritime Services. Please, Carlos, go ahead with your presentation.
Carlos, please activate your.
Carlos.
Now, yeah.
Okay.
Okay, guys. Thank you for your invitation, and it's very nice for me to participate in a high-level event like that. You know, I learned a lot about many issues about the offshore wind farm, Now we'll talk about the mid-ocean and all the application, you know, yeah, I'll share my screen, okay? Everybody see my, okay?
It's coming, just a minute. Yeah, yes, fine.
Okay. Then the presentation that's ready to support planning, installation, maintenance, of course, maintenance and the operation of offshore wind farms, okay? And this is an index, okay? I talk about, let's quickly introduction, life phase of the offshore wind farms and influence of mid-ocean variables in these activities, wind measurement system like LiDARs, the main system, monitoring system for wind with float LiDAR, and I talk about the expertise of the OceanPact group in terms of all item to support the offshore wind farm. Okay, introduction for project the wind farms in Brazil's exclusive economic zone. It's very important, necessary to support the mid-ocean information. The companies help. In the case of companies, we help to choose the more suitable area. The projects in support are choosing the best technology, materials, and size of the wind farm, the dimension of wind farm, and the Brazilian authorities to allow companies and energy action in the future, because we know we need 3 years to continue of doing data in the ocean to have a good place to really operate or install the wind farm, offshore wind farm. The mid-ocean data is largely used in Europe, support assessment wind power generation potential, of course, and also in the US, the mid-ocean data recommended by Bessie and the Boeing, okay, and as a basic stage of the strategic assessment of the offshore wind investment. The mid-ocean characterization recommended practices for US offshore wind energy has the norms and the parameters required by this institution for any analysis, whether strategy, operational, and environmental. In other words, it covers all the information, all the phases of this. This life cycles phase of the offshore wind farms and the influence of mid-ocean variables in its activities. Important to consider in the following mid-ocean phenomena is the several phases of the wind farms. Okay, wind speed, its wind shear on the turbine structure. People talk about a lot about this. Low-level jets here in our figure here, like that. Okay, ocean currents and by wind and by tide, of course, in the area. The principal northeast of Brazil. I talk about a little bit about that. Local tide, low level, high level in terms of the water level. Local waves characteristics such as seasonal and diurnal variation, sea temperature and salinity variation along the water column, and as well the interaction between this condition. Of course, we need to consider all this information, integrate this information, these variables, and of course, surface and subsurface characteristics of the seafloor, because we need to install or directly in the seabed or the seafloor, or you need to anchor the system over there. Well, the life cycle phase of the offshore wind project are planning, 1-2 years continuous. Then in that phase you need to obtain the environment permit. The colleague from IBAMA talk about that. And design, 5 to 8 years. Transport and installation, 1 and 3 years. Operation and maintenance, 2 years plus, of course. And in the end, decommission. One day we need to consider take out everything from the ocean or not. Depending on the situation, depending on the design, depending on many questions. And the planning, the planning phase include the early stage of the product development process, including initial identification, the place, the region, the area, conceptual design, site assessment, and permitting, of course. You need to permit to continue operate. In case of wind, you have the statistic, of course, minimum, mean, means standard deviation, maximum, and distribution in terms of velocity, wind direction, of course, also wind profile, wind shear, turbulence. People talk about a lot this. Develop a reliable power output curves. That's fundamental. Determination of wake effect and assessment of overall wind facility performance, including project loads. Planning, you need to consider also the current and the waves. In that case, I show the AGF radar data from the campus basin, okay? And of course, wave watch 3, the wave model, and buoy to try to fix it in terms of have a good measurement and have a good prediction in terms of waves, okay? The planning continue, then you have to consider also the light frequency. It's very important. Hay and rain, especially the strong one, okay, because this can impact in your offshore wind farm for long term, okay, in terms of fatigue of the material also. In terms of feasibility assessment and conceptual design, you need to consider adequacy of the wind resource, RC water temperature, the bathymetry and site survey of the region, wave condition, current water level, and extreme condition, of course. Permit and environment impact analysis. In the baseline phase, we want to get that different information needed to prepare the environmental report, okay? Besides the biological and socioeconomic aspect, methodology information is crucial at this stage. Besides the local depth, which is very important for wind turbine design, the rest of the process is controlled by methodology condition, as well the condition that can be influenced by the wind turbines and the other components of the offshore wind, like, for example, wake effect. People talk about the Sino, just talk about a little bit about this, but I put this just, you know, to consider this kind of effect on the turbine. Then we need to have a good wind data measurement and prediction also, okay? And I separed this slide because recently I see this operation, the people in the South China Sea, to use the dynamic cable is necessary to match the required operation, the 70 class typhoon condition. Okay, the extreme weather condition is, we need to consider this when you talk about when the design of your offshore wind farm. Exactly, talk about before. Normal condition, extreme condition. You need to consider this definitely in your operation. I put two pictures here. One from my wife, because she has opportunity to visit the Block Island, United States. And the another one is the guy, Dennis Shorley, our colleague. And in terms of design, we need to consider, of course, the shallow or deep water emprendment. In that case, we use this figure from IBAMA to show exactly what's happened when you stay in the shallow water emprendment. The concept model in this area, for example, northeast of Brazil, in the coast of Rio Grande Norte coast, you can see, for example, the current of the longshore current here in green one, the tide current in this yellow one, and the red is the North Brazil current. Okay, that's important. Why? Because the sediment transport in shallow water is very, very important to dimension it. I took this picture from the Landsat image in the London. You can see the wakes of the turbine, exactly because it's shallow water, because a lot of sediment in the region. Then, when you consider to install all the offshore wind farms in northeast of Brazil, the people will need to consider this in the design phase. Okay, transportation installation. For the transportation installation phase, the ocean data are required to support the construction planning, real-time monitoring, forecast during construction. I separated this figure by the Kronos project because in our project we use an integration, the RADIAF radar, satellite data, and in situ data to integrate and assimilate in mathematical modeling in order to have a good forecast in terms of the current and the waves, of course, principle, okay? And this can support your transport and installation operation. All these items here, we need to consider during this phase, because that you have to need a good prediction for this kind of operation. In our case also, we need to generate every day a good reports, a good bulletins that can support all the procedure in case of to have a safe condition to operate in each region, okay? In our case, we have a wind forecast, wave forecast, current forecast. Here is a very nice picture slide, because you can see when you have a combined, we need in this phase of your offshore wind farm, we need to consider for example, the monitoring. We have to collect the real-time data, for example, almost quasi real-time data, and forecast, okay? Because this increases the efficiency of the installation phase. In our case here, I show the AGF radar on left, and the right, I have the mathematical modeling, ROMS, Regional Ocean Modeling System. Then you can combine, you can assimilate this data, of course, the data of measurement, and the mathematical model for improving this modeling, of course, your prediction. It's a similar type of data to the transport installation happening in operation in maintenance phase of your wind farm. Here is, of course, the same to continue. Of course, you have to, for example, to all the schedule of maintenance, the turbine, substation, power cable, every item you need to consider. We need to have an excellent operation window. In that case here, I show the kind of product we provide by Kronos platform, and you have, for example, the data of the wave winds and the current, and depends on your kind of operation. I create a specific operation window for you have a successful during your operation. And the decommission is the last phase of your life cycle. And in that case, it's the same. You can use, for example, the same situation and the operation maintenance. It's the same kind of data we need to use in this phase of decommission. Leaders. This is famous system the people use around the world. Okay, the leaders is the very nice one. You can operate in the 10 to 2,000, sorry, 200 meters. Okay, you have this kind of sample rate. Okay, and you have a range between 1 meters per second or 18 meters per second. The accuracy of 0.1 meters per second. Of course, this is a kind of system we need to calibrate before you install. The same happened with the Leosphere Wind Cube V2. This these two systems domain of the world market in terms of the LiDAR. For monitoring system for wind float leader, well, this float leader is very important system. Okay, here and in this slide, I can show many systems. Yeah, we have a different kind of system. This system use the same all systems use share the same kind of LiDAR. Okay, and if you look here in the table, the most of this system is stage 2. Okay, here I have a picture from different kind one, X-Flider, Wind Sentinel, X-Flider also is a good one, a Full Ocean Sea-Watch. And in the case of OceanPact Geoscience, use the Eólica FLS 200. This another kind one, okay? This the expertise area. The OceanPact group today is ready to support different projects, different phases of the project I mentioned before, in terms of the environment management and consulting, develop of the environment studies, of course, and all phases, the implementation of the program, you can give this support for each one. And in the area of the geoscience, you have the geophysical, geotechnical, environmental, metocean, and surface and subsea position. We have a fleet of the research vessel. This one, the Ocean Tower, is many winch, wayframe, position, everything you want to have a good support. You have a C.O. Johnson, is a research vessel, excellent one also, and included the environmental area and the geotechnical area. Here, some geotechnical investigation, like a seabed sampling, in situ test, offshore soil lab, CPT, piston core, different size of piston core, vibro core, box core, you know, everything you want for geotechnical. In terms of the geophysical investigation, multi-beam is the main system. We have in the hull of the Ocean Tower, you have this system installed on the hull. Then you can operate all along all the Brazilian coast. You have a side-scan sonar, deep tall, sub-bottom profile, it's a seismic, shallow seismic, a magnetometer, and AUV, like a Rugen, 3,000 meters. Oceanographic mooring, lines, installation, metocean buoys. Large inventory of oceanographic equipment in Latin America include gliders, it's an autonomous system, and the profilers, wave tide, current meteorological parameters, real-time data transmission, and in-house processing report. We have also logistics, included the big offshore base in the Açu port. This is a kind of the suite of the metocean monitoring information. You have today, I provided the monitoring by satellite, HVF radar, in situ data, is data by Kronos project. Here is a kind of report, of course, generate, for example, graph, table, dashboard, customized for each client needs. And here to reach in the, we have a partnership of the Eólica company, it's a Spain company. And in our case, we use the Eólica FL 200 float leader buoy. Is passing the test of the offshore wind accelerator, okay? And by part of the carbon thrust, this can give to us the best, you have the best technology for monitoring to collect wind data. This is a view of the system. It's a very cost-effective, versatile, and energy autonomous and reliable. acquire the high-level data, easy transport operation, and in our case, in Brazil, because we have all this infrastructure to support the installation operation of the system, the company today we provide this kind of service in Brazil. This is a suite of the...
Carlos, one minute, please, to conclude, okay?
1 minute, okay. It's a kind of the sensor you have on board of the system, the leader, the power system, you know, the mooring system installation, deployment, data qualification. Of course, conclusion, what happened in Europe and the US to learn the curve obtained by the oil and gas EPR in Brazil will use to support offshore wind project, and this also reflects the environmental issues. Methodology information with measurement generated by numeric modeling techniques play a key role in the phase of the life cycle of the offshore wind farm. And regarding oceanography, the main variables in terrace installation, construction, wind farm, I talk about all these variables. The OceanPact has prepared itself over the last decade to provide the offshore wind farm market with the best service in terms of method-sonographic, geophysical, geotechnical equipment, as well research vessel ready to operate in our region of Brazil coast, offering quality service and, of course, quality health, safety, and environment protocols. And finally, the OceanPact group would be to emphasize that it has an unconditional commitment to ocean sustainability and the engagement to offer its best to the action of the United Nations Ocean Tech. Okay, thank you.
Thank you very much, Carlos, for your nice presentation. It's of course a quick one. Unfortunately, it's an interesting subject that we would like to discuss for a long time. And of course, data gathering, metocean monitoring is crucial for all the phases you mentioned, from planning to design to operation and maintenance. So very interesting presentation. I just one curiosity of mine, because we are ahead of time now. If I understood correctly, the instrumentation that you plan for wave monitoring, I mean, especially long term, because we need the long-term wave monitoring also for fatigue analysis and statistics of reliability of the equipment and so on. So it's based on wave buoys more than, for example, radars or something like that.
In fact, you can use both. You can use the buoy. You can install, for example, wave rider system that you can collect the data for a long time and transmit by satellite, for example, it's possible. Or you can store it inside of the data log system, for example. Or you can use, for example, part of their fleet as a radar system that can collect the wave also, but during the short time period, not during the long time period, you know. Because that nowadays we use the wave watch tree for prediction, but we will calibrate our modeling use this kind of data because fortunately our company has a different system today installed in the Brazilian coast that you can calibrate, and you can use it, for example, sync cost system. There are many information today available if you want.
But insight measurements are always important, even for calibrating the model, right? And especially now that it seems that the conditions are changing in the long term with the climate change and so on.
Definitely. definitely. Yeah. We need to consider when you're planning each offshore wind farm, we need to consider the climate change, definitely.
Okay, thank you, Carlos, once again for your nice presentation. We are about 15 minutes behind our ETA, but I think considering it was a long event this morning, we are fine. It was long, but of course, we dealt with subjects that will be crucial for all of us in the following years, everywhere in the world, from Japan to the United States, from Europe to Brazil. So we have learned a lot. And I will thank once again all the speakers that joined us today and our audience also. And I will pass the ball to Professor Gerente, who's the director of our Committee on Ocean Energy, for his final words and closure. Please, Gerente.
Thank you, Alexandre. And it has been a long morning here, long night in Japan, and long afternoon in Europe, but in US. But I hope all enjoying this event. We are closing the Sobena second workshop on offshore wind and ocean energy. On behalf of Sobena, I would like to thank the invited speakers, the participants, the organizing committee, especially Veronica and Ketsia, and the technical committee on offshore wind and renewable ocean energy. Thanks also to the Sobena technical director, Professor Teodoro Neto. I acknowledge the important support from the sponsors for today's event, OceanPact, the master sponsor, DNV and Bureau Veritas, silver sponsors. The workshop will be soon available on Sobena TV at YouTube. I'm not sure if our president would like to say the last word. And for me, have a good day. And I hope see you soon again.
Last words only to thank you, my friend. Thank you very much, Gerente. And thank you all.
Okay, thank you. Bye-bye. Bye-bye.